In the first unit, as you can see here, we looked at, when analyzing distributions of data, first of all, we were given a graph. If you come across a problem, often you can make a graph of the situation, because usually your data will be just represented as a bunch of numbers. But since it looks like you guys won't be responsible for having to make graphs, they'll be given to you. But we always want to start with a graph. Okay. And then, of course, analyzing it, we use SCIVO, shape, center, variability, and outliers. Okay. And often a numerical summary accompanied the graph that had the measures of center and variability in them. In addition, okay, sometimes the pattern of the observations, the data values, is so regular that we can divide, or we can describe it using a smooth curve. And we've actually done that. You've seen them. You've seen 3 of them. One that's roughly symmetrical, one that's skewed to the right, one that's skewed to the left. Well, those things are called density curves. Okay? So a density curve we use with quantitative variables, okay? And the data values that are represented in the situation are always above the horizontal axis, and 100% of the data values are underneath the curve. That's what this means. It has an area of exactly 1. Because if you convert the decimal number 1 to percent, it's 100%. So we've seen ones that look like this. And I'm going to leave a space here because I'm going to add another. So we've seen ones that look like this, that we called roughly symmetrical. Another way to describe this one that's often used is bell-shaped. We also saw ones that were skewed right and skewed left. Sometimes the data may form like a rectangle. An example of that would be if you randomly selected numbers from 1 to 5. If you did that enough times, all the numbers would be represented in the form of a rectangle. Okay? We call that a uniform. We're going to focus on the bell shape. But that's just another, that is a density curve too. If it goes straight across, and remember what I said, so 100% of the data values are underneath the curve but above the horizontal axis. So all the data values would be like that, and like that. It would all be spread out in here, like so. Okay? And then you do the same thing for the skews to the right and the left. We have seen also, this is kind of a review, that we can find measures of center when we're given a distribution that looks like one of the following. So the median, and I'm not going to worry about the uniform anymore. I'm just going to do the bell-shaped, skewed right and skewed left. well, where is the median located in one of these density curves? It's the vertical line that would split the section underneath into two equal areas. So if it's bell-shaped, from the horizontal axis to the peak would split that. So that would be the median. And then we saw that if it was skewed right, it gets pulled right, but not very much, if at all. So it might go a little right, but not very much. Same thing, the reverse if it's going left. So that's where the median would be located in those density curves. The mean is a little bit different. You have to think of it a little differently. You have to imagine the section underneath as like a block of wood. And the mean balances the block of wood. So if it's bell-shaped or symmetrical, the mean would obviously be in the middle again, from the horizontal axis to the peak. Okay? If it's skewed right, the mean's going to get pulled right more than the median. And then the opposite's going to happen if it's skewed left. So we've seen that. We did refer to that in Unit 1. So very quick question. Here you have a distribution that is what shape? Skewed right. Where would the mean and median be located according to what letters? Mean would be C and median would be B. So the median would be B because they both come off the peak if it's skewed. But the mean more so than the median. Okay, we're going to focus on the bell-shaped one. And it is called, this distribution is given a specific name. It's called the normal distribution. And this is called the normal curve. Okay, because, and remember, all the data values are all in here. Much of what can be described in real life follows a normal distribution. For example, test scores. Okay, in general, most test scores, you'll have some high marks, you'll have some low marks, and you'll have the majority in the middle. That follows a normal distribution. So things like here, I've written down here, SAT scores or IQ scores. Rolling a pair of dice. Well, the probability when you roll a pair of dice, it's a pretty low probability to get a 1 and 1 or a 2, as well as a 6 and 6 or a 12. The one that appears, the one where the probability is the highest of rolling if you roll 2 dice is what number? What do you think? 7, right? So we would get 7 a lot of the time, and then we would get 8 and 6, and then 5 and 9, and etc. Okay. Whenever you're measuring something, okay, you won't get the same exact measurement if you measure something over and over again. Sometimes you get a little higher. Sometimes you get a little lower. Sometimes you'll get a little bit too much higher, but not very much. Other times you get a little far too low, but not very much. Follows a normal curve. Populations. follows a normal curve. Okay, a lot of what we're going to be studying in this course follows a normal distribution. So a normal curve is bell-shaped and symmetric. We are going to focus on the mean, not the median. So the mean is located at the exact center. So the mean would be located here. And the standard deviation, which we'll find out in a second how to find on a normal distribution, measures how spread out the data is. Okay. How do we find standard deviation? Now, it's easy to find the standard deviation in the one above, but here's, if you had to draw and label a normal distribution, which you're going to have to do, then given a situation. It's pretty easy to draw that. Pretty easy to find the mean. It's right in line with the mean. Okay. And then the data spread out. So it's going to be one standard deviation above, two above, three above, 2.5 above, whatever. And then it's going to be below. The question is, how far do we do one standard deviation? Well, what you do is you do it in relation to the curve, and you may know this from AP Calculus or Intro of inflection points. Okay? An inflection point is when a curve goes from what we call concave down to concave up. So like if you're going down like this, and then you start to come up like this, okay? A lot of times you can actually feel when you start to come back up. It's about halfway down the curve. So about halfway down the curve, here would be one standard deviation. It's not up here. It's not way down here. And then about halfway down the other side, because it's symmetrical, would be one standard deviation. So here's our mean. That would be one standard deviation in either direction, below the mean and above the mean. How do you find two standard deviations? Well, now that you know how far it is from the mean notch to the one standard deviation notch, just go the same distance. And to find three, just go the same distance again. So I'm going to have to extend this. So this would be two standard deviations above and below. And this, oh, wrong one. Would be three standard deviations above and below. So if we go back up here, we would see
that this is one standard deviation. This is 2. This is 3, and that's above. And notice if you went from one standard deviation, and if you drew an imaginary horizontal line up, it's not very accurate. Let's try that again. You're about halfway down the curve. Okay, so that's how you get the first standard deviation, and then you get the second and the third by looking at the distance between your mean and first notches. So what would a situation look like? Well, here's an example. You're given a normal distribution, a normal curve, and you're given the notches that will represent the mean and 1 standard deviation above below, 2 standard deviation above below, 3 standard deviations above below. So IQ scores are commonly thought to be normally distributed. And the mean is 100 points, the standard deviation is 15 points. So basically what you do is you're asked to label. First off, when we label a normal distribution, you need a label for your horizontal axis. In this case, we are measuring IQ scores. We know where the mean's located. What's its value here? 100. We know that 1 standard deviation is represented by 15 points. What would this value be? What would this value be? 130. And this value? 145. Starting from the mean again and going down, this value? 85. 70. 55. So that's a completely labeled normal distribution. Because a lot of times when you do normal distribution problems, you're going to have to draw a diagram to accompany your solution. Okay? Okay. What about the data values themselves? In a normal distribution, okay? In general, approximately, do I have the color? Or if I can match the color. 68% of all the data values in a distribution will fall within 1 standard deviation of the mean. 95% will fall within 2 standard deviations. And 99.7% will fall within 3 standard deviations. So there's a few data values left, but very few that fall outside. Those are very extreme values. Okay. And we can use this knowledge to answer questions about distributions. Okay? So when we have normal curve or normal distribution problems, first of all, we want to draw and label a normal distribution curve. Perform any calculations using these values. We'll see in a second. And answer the question always in the context of the problem. Okay? Let's do one. We're back to the IQ score. We know that it looks like this. And we saw the values. 100, 115, 130, 145, 85, going the other way, 70, 55. So we're going to use this distribution and what we just learned above to answer this question. What percent of the test scores were above 7? So what I want to find is I want to find that section. Well, here's how we can do it. The 70 is how many standard deviations below? 2. And this is 2 above. What area is this? 95% within 2 standard deviations. So this is 95%. But I haven't accounted for this little section here. Okay? Well, drives me nuts why it does that. If this is 95 within 2 standard deviations, what percent is outside? 5%. Both of those are represented by 5%. But I don't want to include this section. I only want to include this one. So therefore, I would add 5% divided 2. Because these are 2 equal sections. Together they're 5%. Each one is half of 5%. So that would give me a final answer of 97.5% of the scores are above 70. So we're using, and you notice at the top, what's called the empirical rule, those 3 numbers. Oftentimes it's just called the 68, 95, 99.7 rule. You just got to remember those 3 numbers. Okay, and you can answer those answer questions like these. So here, you were given a score, asked what percent above. You may be given or asked to work the opposite way, like this question. Again, I've got to draw my distribution. Q scores, students often forget the label. Notice. They remember to label the values of each notch, but forget to label the horizontal axis. Okay. Which score is at the 84th percentile? That means at which score is 84% of all the scores the same as that score or less? Remember, that's what percentile means. So 84% is going to be something like that, but I don't know. I'm trying to figure out what value this is.
I got to use those numbers above to help me. So it's kind of like solving a puzzle.
Well, maybe we can answer, like, I know it's going to be here, and I know, like, here, I'll just put this in and then erase it. I know that at 100, 50% of the scores. But I want to know 84% of the scores. So it's going to be somewhere here. Okay? So why don't we try 115? How many standard deviations away? 1. So 1 standard deviation below means that what percent's in here? 68. Now I need to find out what section's in, or what percent is in now. Well, what percent is in these two?
32.
32. But in half of it is 16%. So 68% is here. 16% is here. And if I add those two up, I get 84%. So that means this section here is 84%. I found the percent I'm looking for. And it happens at the score of 115. Does that make sense? Right? So what you can always do is you start with the middle. When you answer a question like this, like if it said, you know, what percent of the scores, or sorry, which score was at the 16th percentile? Well, start at 50, and you know that 50 is below, so it's going to be one of these that gives you the answer. A score of 115 is at the 84th percentile. Okay. We're going to be answering a lot of questions like this. Okay, because like I said, a lot of statistical problems that we address involve normal distributions or using a normal distribution and probability to help us answer. Okay, right now, you're kind of limited in the questions you can answer, because what if I asked you, I said, okay, what percent of the scores are below 105? Now I can't use those numbers, can I? Because 105 is here. I don't know what percent that is. Well, that's the next lesson where we use a graphing calculator to help us answer that. So make sure you have that next week, please, for next class. The discussion talks about IQ scores. And there's a lot of controversy around, actually, is it possible to measure intelligence? Like, how is intelligence defined? Is it book smarts? Is it street smarts? Is it a combination of both? Is it how much you learned in school? Or is it how much your reasoning capacity is? Who knows? Okay. So these guys in 1994 came out with this book and discovered, or made the conclusion, that Black people score about 15 points lower on IQ tests than white people. That's a pretty bold statement. Okay. And some people, unfortunately, still believe this. But it's really been debunked, because if you think of it like this, Here's the test that they used. It's called the Air Force Qualifying Test. Okay. Here's a question from it. They figured that was a good IQ test. But here's a couple questions from it. So, understanding what the word solitary means. Or a mathematical problem where you're given a shape, you're given some information about the shape, and you're asked to find some missing, or you're asked to find some missing information. One could argue, are these really measuring intelligence? Especially this one. Like, would this just sort of come naturally in your natural reasoning growth? No, you would learn this in school. So it would be prior knowledge. So those who have that prior knowledge or access to that prior knowledge would have an advantage. So a lot of people argued, they said, well, perhaps more white people had access to better education. Therefore, they did better. And that's why this was debunked, because it's like, how do you measure intelligence? And that's an argument that still goes on. You know, I mean, everybody's heard of IQ tests. You hear Trump brag about his apparently sky-high IQ. Okay? You know, but what was his IQ test? To be able to repeat 5 words like horse, elephant, things like that? Who knows? Okay? But it's interesting that because intelligence is measured using a normal distribution. But can you really measure intelligence? And has there been anything developed yet that people would agree, okay, yeah, this measures intelligence? So that's what that discussion is.